So today's lesson is going to be on Graham's Law, where we are talking about the movement of a gas. Now, we could talk about the movement of a gas in terms of diffusion or in terms of effusion. Both of these are moving of gas particles. The difference is diffusion is moving in a closed system in order to get the equal distribution of particles in that system. Effusion is the movement of a gas through a hole. For example, if you were to run over a nail with the tire of your car and create a hole in the tire of your car, air is going to leave the tire of your car. That is effusion. Remember, kinetic energy is determined by temperature. As temperature goes up, so does kinetic energy. As temperature goes down, so does kinetic energy. Now, if temperature and kinetic energy are the same, then heavier molecules are going to move more slowly. So Graham's law is the relationship of a comparison, really, of how molecules move based on their molar mass, as long as temperature and kinetic energy are held constant. So those two things must be the same in order for Graham's law to work out. Graham's law states that the rate of diffusion is inversely related to the square root of the molar mass of a substance. So the rate of gas A over the rate of gas B would equal the square root of the molar mass of gas B over the molar mass of gas A. So it is an inverse to the square root. So let's do a couple of practice problems. All right. Which gas diffuses faster at the same temperature? Carbon dioxide or xenon? And we want to know how much faster it diffuses. So, when we look at our periodic table, and we use the periodic table to determine the molar mass of carbon dioxide, 1 carbon and 2 oxygens, we are going to get a molar mass of 44.01 grams per mole. And xenon, according to our periodic table, is going to have a mass of 131.29. All right, so we want to know how much faster it moves. So that means we want a value that is larger than 1. So in order to set this up and to get a value larger than 1, I am going to put my heavier molecule or my heavier mass on top. And I'm going to put my smaller on bottom, and I'm going to square root it. So essentially, the rate of carbon dioxide compared to the rate of xenon equals. All right, we are comparing carbon dioxide to, and that kind of looks like Ca. Let me make that more clear. CO2. All right. Now, what we have to do is we simply have to plug this in. The square root divided by of 131.29 divided by 44.0. So when I plug this into my calculator, I'm just going to square root 131.29 divided by 44.01, and that gives me a value of 1.72719. All right, so when we are worrying about this and we're doing this here, let's go out to 3 sig figs, 1.73 So what does that mean? That means carbon dioxide diffuses 1.73 times faster than xenon. All right, let's look at our next problem. Which gas diffuses faster at the same temperature, nitrogen or ammonia? All right, and ammonia is nitrogen trihydride. So ammonia is the common name, but its name according to our IUPAC system we learned in class is nitrogen trihydride. So step one, when I find the mass of nitrogen, now remember nitrogen is diatomic in 2. So it's going to have a mass of 28.02 because there are 2 nitrogens. Ammonia, 1 nitrogen plus 3 hydrogens is going to give me a mass of 17.04. So I know that ammonia is going to move faster because it has the lower molar mass. So I'm going to arrange the rate of ammonia over the rate of nitrogen. Now it's going to be related to the inverse of the molar mass. So I am going to put the mass of nitrogen on top, 28.02, and the mass of ammonia on bottom. And when I solve for this in my calculator, I get 1.28. So what does this mean? This means ammonia diffuses 1.28 times faster than nitrogen. All right. So let's do our final practice problem. An unknown noble gas. All right, so now that's good because it's telling me where on the periodic table I'm going to go to find that. And remember, our noble gases are group 8A. So we're looking at one of these options in group 8A. It diffuses through an opening at a rate of 0.0165 times that of helium. All right, so what is that? My number is less than 1. So essentially, because my value is less than 1, this is saying that the noble gas is moving slower than helium. All right, so what I've got to do is I have to set it up. My noble gas is going to move slower than helium, meaning helium has the smaller molar mass. So helium has a mass of 4, and we are trying to solve for the molar mass of the unknown. And by taking a large value and putting it on the bottom and the smaller number on top, that will give us a value less than 1. So this is equal to a value less than 1. Now, so maybe I should make this look a little bit neater for us. So 0.3165 equals. So what is my first step going to be? My first step to get rid of this square root sign, I'm going to square both sides. So when I take 0.3165 and I square it, I get this value 1.0017, this big old value. And when I square a square root, the square root goes away. So essentially what I have here is I have this value equals 4 over the molar mass of the unknown. So now I can solve for the molar mass of the unknown, and when I rearrange my equation here, to get molar mass by itself, the molar mass of the unknown by itself, I end up with 4 divided by 0.11017. All right, so now let's solve. We are going to do 4 divided by our answer. All right, and notice that I am not rounding or doing anything like that, and that because if we were to just put in 4 divided by 0.1, we might get a different answer, okay? That doesn't make sense. So here's our answer, 39.93. Molar mass typically goes out 2 decimal places. All right, so let's find that. And the mass was put in our correct units here. What element in the noble gas has a molar mass close to 39.93? And we find that to be argon at 39.95. So we are looking at the gas of argon.